Okay, class, we're still talking about action potentials. In the last video, we described all the steps. Let's think about it. We described all the steps that occur in an action potential. Okay. What I want to discuss now is something we call the absolute and relative refractory periods. The absolute and relative refractory periods. Okay. The action potential just described occurred on one spot of the neuron membrane. That one spot needs to rest before another action potential can be created there. So what I'm saying is that one spot that one spot that the action potential occurred in, let's say this, needs to rest before another action potential can come. That rest period are called the refractory periods. That rest period, there are two of them, would be the refractory periods. So let's see what we got. What we have is the absolute refractory period and a relative. The absolute refractory period is a time that it is absolutely mandatory for that spot, come here, I think, space there, for that spot, for that spot of the membrane to rest. A time is absolutely necessary for that spot, we'll put on the membrane to rest and not perform another action potential. Absolutely. The relative refractory period is a time another action potential could occur on that spot, on that one spot. Okay. So this is brand new, so we're just getting it together. So when you print it out, see, it'll be all straight. That could occur on that one spot, but the voltage needs to be higher than the usual threshold voltage. So it's relative. So absolute, it cannot occur at all. Relative, it can, but you need to give a higher than threshold voltage. Okay? See, here's the action potential. So absolute and then relative. Okay. What causes the absolute refractory period? The absolute refractory occurs when the voltage-dependent gates, and I should put when the sodium voltage-dependent gates, it's not the potassium, when the sodium voltage-dependent gates have not been reset from the currently occurring action potential. So again, when the sodium voltage-dependent gates, not the potassium, when the sodium voltage-dependent gates have not been reset from the currently occurring action potential, the ones that's in progress right now. Since the sodium gates are responsible for the initiation of the action potentials, see that, remember, the action potential started because threshold voltage opened the activation gate real quick. That started the whole thing. So until you reset it, and see right now, we turned our attention away in this action potential. Think about it. We turned our attention away. So it's kind of like you had a stage play. Let's think about it. You had a stage play. The first actors are on. Then scene one is over, and you're now looking at scene two with a second set of actors. Well, what are the first set of actors doing? See, we're not talking about them anymore because we got the second set. The first set of actors are redressing for the third scene. So assume now, when we got down here, let's go here to a better one. When we got here, we talked about potassium. We stopped talking about sodium. Sodium had gone into the background. But what's sodium doing during this time, that potassium, is resetting the gates. What does resetting the gates mean? Closing back the activation gate and opening back the inactivation gate, which is what it was like at first. So until that occurs, you can't start another action potential in that same location. So it is that gives the absolute refractory period, the time to reset the sodium gates. Right? Now let's go to the relative. What causes a relative? When the potassium gates are opening, now see, the relative has to do with the potassium, are open, allowing potassium to come out. But remember, when potassium's coming out, you're going down this way. Threshold voltage is up this way. So when potassium is coming out, you're making the inside what? More negative. But to get threshold, you have to make it more positive. So when the potassium gates are open, allowing potassium to rush from the cell, make it interior more negative, any stimulus to reach threshold has to be stronger. Why? The interior of the cell is getting more negative, and threshold voltage requires the interior to get more positive. So the outrush of potassium is counteracting the reaching of threshold. That's what the relative refractory period is about. So we have two refractory periods that say on that one spot, you can either not do it at all with another action potential, or you can, but you have to give a stronger voltage. Okay? That's what that's about. Now we go to, how does conductivity? Remember, all of this was happening on one spot. Now, how do we get this thing to conduct? How do we get this thing to conduct? How do we get it to move? How do we get it to start here, then move to the next spot, and then move to the next spot, just like an electric wire? How do we get this conductivity to occur? Let's look at this. An action potential occurs on one spot of the neuron cell membrane, but what causes it to move, propagate along the membrane, like an electric wire? Okay. Voltage-dependent gates along a neuron cell membrane are very close together in the axon cell membrane. Now I'm coming back here. We kind of talked about the neuron, but I want to talk about it again. Let's go back and find one here. Here we are. All right. We said dendrites, cell body axon. It is here that the voltage-dependent gates are close together. It is here that action potentials occur. Back here, graded potentials, we'll talk about in a moment, occur. So it is here that action, that's where the voltage gates start, right here at something called the axon hillock. So we're talking about the axon, okay? Voltage-dependent gates along the neuron cell membrane are very close together in the axon membrane. The axon is a portion of the neuron. The voltage change due to an action potential, let's say due to an action potential, creates a charge field. Now, wherever you have a charge, and this is true, you create a charge field. That's why sometimes they say don't play around electric wires, because there is a charge field. Even though the wire has been insulated, there still can be a slight charge field. Okay? Creates a charge field around the spot of action potential. The charge field causes a voltage change in the adjacent segment of the membrane. See, this right here is where the charge, but that charge is causing a voltage change, that charge field. Okay, the voltage change of the new action potential. Okay, enough. Okay, let's go back. The charge field causes an adjacent. This voltage change is enough to reach threshold voltage in that next area. Okay, this was in that adjacent segment, thus starting an action potential in the adjacent area. Because see, the voltage here, when you kick this up, because remember, this membrane took over everything. Then that voltage, so there was a charge field. That charge field is being perceived by the next area. See how this charge field, see how all that is? So now we start to get that charge because of this. Causes next to start another action potential. This action potential repeats itself all along the cell membrane. So one area lights up another area. Then that area lights up another area. Thus moving the action potentials along the membrane like electricity moving along an electric wire. So that's how it occurs. Now there's another factor playing in on this that helps this occur. Okay? So let's do this. This will help further understand how it's able to light up that next area. All right. What is the all or none factor in action potential? Now let's go back there. We said that the all or none was that no matter that if you didn't give threshold voltage, you didn't get any of this stuff. If you did, you got this. If you gave above a threshold voltage, you still didn't get any higher. So let's see what we got. The action potential is all or none. This means the voltage height of the action potential gets no higher despite the magnitude of the threshold voltage. If the threshold voltage is a positive 40, then no action will be created if less than 40 is given to the membrane. However, no greater size action will occur if more than 40 is delivered. So I'm just picking 40 as just something to say. Okay. In order to see its significance, let's examine the axon of a neuron. The axon is a long structure, and action potentials move along all the way to its end. Okay, let's go further. Let's think of analogy. This is my analogy. Imagine you had an opened out metal coat hanger. So you went and got a coat hanger, opened it out, undid it, opened it out. And then you went and pulled a firecracker fuse off a firecracker. You're going to cut the firecracker fuse the same length as you have the straightened out metal coat hanger. We then get a candle and a cigarette lighter. We touch one end of the metal coat hanger to the tip of the wick of the candle and use the cigarette lighter to heat it up the other end. If we put our finger on the end of the coat hanger where it's being heated by the cigarette light, it is very hot. But as we move our finger further along towards that candle, it gets cooler. It gets so cool that there's not enough heat to cause the candle wick to reach the kindling temperature. Thus, the candle wick does not light. So the coat hanger couldn't do it because by the time the heat had dissipated away from that length of that coat hanger, it wasn't enough heat to light the candle wick. Why is this? The heat spread along the coat hanger is a passive spread of heat that diminished as you did. On the other hand, we now do the same thing with the firecracker fuse. Because of the construct of the firecracker fuse, the heat of the cigarette lighter will cause the firecracker fuse to light up, to burn, to the same extent all along the way, because the one area lights up the other area. But the way it works is there's a constant heat to the same magnitude. This means the heat will generate all the way to the fuse to the end. The candle wick being touched by the firecracker would definitely light up. This is an all or none event, because if the cigarette lighter had not lit up the firecracker fuse, nothing would have happened. But if it did light it up, the candle wick would light up. The heat spread along the firecracker is an active spread of heat that stays in a constant intensity all the way to the end, which is the same thing this does. Which is because the action potentials are all or none, it ensures the action potential will go all the way. So you see, if the action potentials were like this, and then the next area did this, and then the next area did this, then by the time you got to the end of this thing, you wouldn't have nothing. Because if the first one's big, then the second is small, and the third, you wouldn't have nothing because it would have damped out. And it would have not taken it all the way to activate another neuron when we get to it. Okay, so read through this. These are kind of things that aren't really in the book to explain what the significance of some of the stuff is. That's why I wrote this document. Okay. So now we're going to close this video here because now we're going to skeletal muscle. Skeletal muscle resting membrane potential and action potential. And I'm going to put and its action potential. Okay. Okay. See, when you get this document, it'll be all corrected. We'll correct it as we read. All right. So we're going to close this right here. And that's where we're going next.